What if I told you that one of the most extreme things in the universe isn't a black hole at all? Instead, it's an object only about 25 kilometers wide, yet a single teaspoon of it weighs more than 1 billion tons. This sounds like science fiction, but it's real. It's called a neutron star, a cosmic monster born from the explosive death of a massive star. Today, we're diving into how these stars form, what's inside them, and how their violent deaths created many of the elements on Earth, including the gold you might be wearing right now. Every star in the night sky survives because of a delicate balance. Nuclear fusion inside the core pushes outward with tremendous force, while gravity tries to pull everything inward. As long as hydrogen fuses into helium, a star remains stable, but eventually that fuel runs out. Smaller stars like our sun will expand, cool, and fade into white dwarfs, but stars that are many times larger experience a much more dramatic ending. When helium is gone, gravity squeezes the core tighter, heating it enough to fuse heavier and heavier elements: carbon, neon, oxygen, and silicon. Each stage burns faster than the last until finally the star produces iron, an element that cannot release energy through fusion. When the core fills with iron, the internal balance collapses instantly. With no fusion left to counter gravity, the core collapses in a fraction of a second. Electrons and protons, normally kept apart, are crushed together to form neutrons. The entire core, once the size of Earth, shrinks down to the size of a city. Meanwhile, the outer layers fall inward, crash into the solid neutron core, and rebound outward in an enormous explosion called a supernova. This blast can outshine entire galaxies. And when the smoke finally clears, what remains at the center is a neutron star, a tiny, ultra-dense sphere made almost entirely of neutrons. A neutron star is one of the most extreme objects in existence. It has the mass of 1 million Earths squeezed into a ball only 25 kilometers wide. Its gravity is so strong that it bends light around its surface, letting you see parts of the backside. A sugar cube-sized piece of neutron star material would weigh more than 1 billion tons on Earth. Temperatures on the surface reach over 1 million degrees. And if a neutron star were just a little denser, it would collapse into a black hole. Even dropping a pebble from just 1 meter above the surface would make it hit at close to the speed of light, exploding with the energy of a nuclear bomb. Despite being small, the inside of a neutron star is incredibly complex. The outer crust is made of iron atoms squeezed into an extremely strong crystal lattice. A mountain on a neutron star is only a few centimeters tall, yet it weighs more than the entire Himalayan range. Deeper down, pressure forces atomic nuclei into bizarre shapes. Long rods, flat sheets, and twisted structures, known collectively as nuclear pasta. Scientists believe this may be the strongest material in the universe. At the very core, the pressure becomes so intense that neutrons may break down into quarks, forming a dense soup unlike anything found on Earth. Some theories even suggest the existence of strange matter, something we still don't fully understand. Neutron stars are also incredibly energetic. When they form, they spin extremely fast, sometimes hundreds of times per second. Their powerful magnetic fields shoot out beams of radio waves that sweep across the universe like cosmic lighthouse beams. When these beams cross Earth, we detect a regular pulse, giving these stars the name pulsars. Some neutron stars have magnetic fields so strong they can tear atoms apart. These are called magnetars, and a single flare from one can release more energy in a second than our sun produces in 100,000 years. But the most spectacular events involving neutron stars happen when two of them orbit each other. As they circle, they slowly lose energy by emitting gravitational waves, literal ripples in the fabric of space-time. Over millions of years, the stars spiral closer together until they finally collide in a massive explosion known as a kilonova. For a brief moment, conditions become so extreme that heavy elements like gold, platinum, and uranium are formed in enormous quantities. The jewelry you wear today was forged in the final moments of two dying neutron stars. After this dramatic collision, the two stars usually merge into a black hole, a final death after an already violent life. The material thrown out by these explosions drifts through galaxies for millions of years. Eventually, gravity pulls it into new clouds of gas and dust. These clouds collapse to form new stars, new planets, and new solar systems. Our own solar system was born from such a cloud, enriched by the remains of ancient stars and neutron star collisions billions of years ago. So when we study neutron stars, we're not just looking at distant cosmic objects.